Alright, so we're going to wrap up this chapter with one of my most favorite topics, which is implicit derivatives. Here's the idea. We've actually been taking implicit derivatives the whole time. Let's say I write y equals x squared, and I ask you to find the derivative of y equals x squared. Well, you know that that's dy dx equals 2x. But what if I told you we were hiding something? There's a little piece that's been invisible the whole time. When we take the derivative of x, we actually need to write dx dx. Because when you're taking a derivative, you're taking it with respect to a variable, and you're asking how does this variable change with that variable? So how does y change with x, dy dx? Then when we take the derivative of x squared, we need to say how does the top variable x change with x? Now, because dx dx is 1, we don't write dx dx. We just write dy dx equals 2x. And the reason for that is because a variable moves with itself. That's just what happens. The variable moves with itself. But we can use these implicit derivatives to do really, really cool things. Let me show you this example. This is a very interesting curve that's probably not a function because it's y squared. Whenever we mess with the y variable, we tend to make things not be functions anymore. However, with implicit derivatives, we can still very easily find the slope and the instantaneous rate of change at any given point. Let me show you how. The rule is this when you're doing implicit derivatives. When you take the derivative with something with respect to another variable, you need to write dy dx. You need to write d whatever over d of the variable you're taking the derivative of over the derivative that you're taking it with respect to. I know that's a little confusing. We'll do an example. If it's just the variable that you're taking the derivative with respect to, like the dx dx, then you don't need to write it. So only when it's another variable do you need to insert the dy dx, or dh dx, or dp dx, or whatever it is. So let's find this implicit derivative. Here we go. First, you take the derivative. The derivative of y squared is 2y. However, we're taking the derivative with respect to x, and so I need to write dy dx. I need to insert that slope. Minus, the derivative of x cubed is 3x squared. Now, do I need to write dx dx? No, because dx dx is 1. Finally, the derivative of 28 is 0, and I don't need to write dx dx or anything like that, because a constant is just 0. So that's it. We have 2y dy dx minus 3x squared equals 0. That's all we have to do. Let's go ahead and solve for dy dx, and we'll have our derivative. We add 3x squared to both sides. So 2y dy dx equals 3x squared. Divide by 2y on both sides. See how I'm just treating the slope like it's a variable. Just treat it like it's a variable. Divide by 2y, divide by 2y. We get 3x squared over 2y. So notice that our slope depends on both the x variable and the y variable. So that's kind of cool. This is called the differential equation, where we have an equation with a derivative in it. Now, to find the slope at the point 2, -6, you just plug in 2 and -6 into your equation, and then you're done. So dy dx equals 3x squared, so I plug in 2, 3 times 2 squared, all over. On the bottom we have 2y, so I do 2 times -6. That's going to equal 12 over -12, which is just equal to -1. So this curve, which I don't even know what it looks like, it's probably not a function because it'll double back on itself probably. However, the slope at the point 2, -6 is equal to -1. So the big takeaway is treat the derivative like its own variable. In fact, I sometimes like to write y prime instead of dy dx, and then just solve for dy dx, and then just plug in your point and you can find the slope. In the next video, we'll look at another example.